This time I want to talk a bit about the difference between the open loop gain and the closed loop gain, and then look at how we characterize op-amps in terms of their frequency dependent performance, and get some real data from a datasheet of an actual device. First of all, because it's often a point of confusion, I need to make sure that everyone is completely clear on the difference between the open loop gain and the closed loop gain of an op-amp amplifier. First, the open loop gain. The open loop gain is a function of the op-amp itself. Put an op-amp in a circuit, there will be some voltage on its non-inverting input, there will be some voltage on its inverting input. The difference between these two voltages I've been calling VD, the difference voltage. The output of the op-amp, Vout, is proportional to the difference between these two input voltages, VD. Vout equals A times VD. That is the open loop gain. It's not a function of any of the other components around the op-amp. It's purely a function of the op-amp itself. However, if I was to build an amplifier using this op-amp, maybe I was going to build a non-inverting amplifier with a gain of, let's say, 5. I might put a 4K resistor there and a 1K resistor down here. That would give me a gain of 5. I would have V in here and V out here, and V out over V in. That is the gain of the whole amplifier. An amplifier built using an op-amp. This is a gain including the effect of this feedback that comes through this 4K feedback resistor. So this is what we would call the closed loop gain. It's the gain after we've closed the feedback loop. Note that the closed loop gain is a function of the resistors that you place around the op-amp. It's a function of the whole circuit. The open loop gain is a function of the op-amp component itself. We derived a formula for the closed loop gain of a non-inverting amplifier like this before. And in terms of the 4K and the 1K resistor here, we would have written that Vout equals Vin times 1 plus 4K over 1K, which is therefore 5 times Vin. The formula being that the output voltage is the input voltage multiplied by this resistor. I'll call it RF, the feedback resistor. This divided by this resistor, I call it R2, for want of anything better to call it, plus 1. But to derive that formula, we had to assume that the open loop gain of the op-amp was practically infinite. And what we're finding out now is that that is a good approximation at low frequencies, but it's not a good approximation at high frequencies. Because at high frequencies, the gain of this amplifier turns out to be a function of frequency, and it drops at higher frequencies. To determine exactly how, we have to use our new formula for the open loop gain as a function of frequency, which is the open loop gain at DC divided by 1 plus J F over F. I've called it FD in this slide rather than FB, but it's a characteristic frequency of the op-amp itself. And rederive this formula, not assuming that the open loop gain is practically infinite, but assuming that the open loop gain is given by this expression. And we'll be doing that in the next video. What I did want to do in this video is have a quick look at the datasheet of a typical op-amp, because you might be surprised at the actual value of FD, a frequency at which the open loop gain of the op-amp starts to decrease. If you look at this formula, AF is ADC over 1 plus J F over FD. If F is very, very much smaller than FD, then this term here is going to be negligible compared to the 1. We're just going to get the open loop gain is equal to its level at DC, its low frequency value. If FD is much bigger than F, however, then this term here is going to be much, much bigger in magnitude than the 1. We can neglect the 1. And now we have a open loop gain which is very much dependent on frequency. In fact, it's inversely proportional to frequency. The frequency at which this reduction in the open loop gain starts to have a significant effect is going to be around about this 3 dB frequency, around about the value where F is equal to FD. Now we use op-amps for a wide range of circuitry, and a typical op-amp that we use a lot in the lab is the TL071. We use these for audio frequencies quite happily. So you might be surprised to learn that the value of FD for a TL071, according to its datasheet, is about 15 Hz. The relevant graph, taken from the datasheet, looks like this. You'll see that the open loop gain here starts off at a very high value, around about 200,000, but it starts dropping at about 15 Hz. This is actually fairly common for op-amps. They have capacitors inside them which starts the open loop gain dropping from comparatively low frequencies. If you're interested in why the open loop gain of the op-amp starts to decrease from such a low value, it has to do with the stability of the op-amps. I'll say more about this later, but just to give you the general idea at this point. Supposing I had a non-inverting amplifier that looks like this. The effect of that internal capacitor causing the drop-off of the open loop gain at these frequencies is to introduce a 90 degrees phase shift between VD, the difference between the two input voltages, and the output voltage. So I've now got a 90 degree phase shift through the op-amp itself. Now, there are going to be some stray capacitances around in the circuit. If nothing else, the op-amps have a small input capacitance themselves. So if we just assume this is an ideal op-amp and draw the internal input capacitance of the op-amp outside it for now, there's a small capacitance here. This means that our feedback system is now from Vout down through a capacitor and a resistor in series. This is a reactive network now. This is going to introduce another phase change, so that the input on the inverting input there is no longer at the same phase as Vout. There are other effects around in the op-amp as well, all of which can increase the total phase change between the inputs to the op-amp and the feedback signal that's come all the way through the op-amp, back through the feedback resistor there and down, and is going back into the op-amp. Now, in order to get a stable amplifier, we need this to be negative feedback, so that an increase in VD causes the output to move to try and reduce that value of VD again. But if the phase difference around the feedback loop is too great, then that doesn't happen. The problem comes especially when the total phase change around the entire feedback loop ends up at 180 degrees. And if that happens, we no longer have negative feedback. We have positive feedback. Because if you take a sine wave and you move it in phase through 180 degrees, you end up with this. The sine wave upside down. So the signal that we would like to have here in order to reduce Vout is actually acting to increase Vout. Our negative feedback, which we need for stability, has become positive feedback. Well, if the gain of the op-amp, when this happens, is greater than 1, then we no longer have a stable amplifier. We have an oscillator. Because any small amount of signal at that frequency will be amplified up as it goes round this feedback loop, getting bigger and bigger and bigger until the output is dominated by a large oscillation. So it's important for any circuit like this, built on any circuit board in which there may be any stray capacitors around, that the total phase change around the feedback loop and through the op-amp doesn't exceed 180 degrees when the gain of the op-amp itself is greater than 1. And since the gain of the op-amp starts off at such a high value, about 200,000 in this case, and we need to get it down below 1 by the time the phase change is 180 degrees, that means we have to start it moving down really quite early. Is all of this a problem if we want to design an audio amplifier with a bandwidth up to 20 kHz or so, and all we've got is a TL071 whose open loop gain starts to decrease at about 15 Hz? Well, usually no, it's not a problem. And we'll go on to discuss the reasons why that is true next time.